Welcome to Lesson 11, Radical Expressions and Rational Exponents. So in this lesson, we are going to build on the processes we use to simplify square roots, to simplify higher order roots, cube roots, fourth roots, etc. And then we're also going to talk about how radicals, square roots and cube roots, etc., can be written in exponent form and then work with that form. So we'll start by applying our processes that we use to simplify square roots to cube roots and higher roots. I just laid out here in the table, I don't know why cube roots are there twice, but basically the same idea as with square roots. If this is a square, so there's no 3 there, then that means that b squared equals a. So if there's a 3 here, it means b cubed equals a. A fourth root would be b to the fourth is a, etc. Okay, so we call this number right here the index. So for a cube root, the index is 3. For the square root, a lot of times, actually, why don't I just kind of write it like this? Maybe that's what I meant. If there's nothing there, then the index is 2 because that's a square root. One other thing I just wanted to point out before we do these quick examples is that there is a word, I think we mentioned it before, but whatever is underneath the radical symbol is called the radicand, which is a weird word for sure. I'll just write it out. The thing under the radical. And the reason that's useful is just because it's a lot shorter than saying, oh, this thing underneath the square root or the cube root. You just say radicand. So that's a word I'll probably refer to as we go through this. So for example, just like the square root of 9 is 3, right? The cube root of 216 is asking you what number times itself 3 times equals 216. The answer to that is 6. And it might be helpful for you to make kind of a list of numbers and all of their powers up to at least 4, maybe even 5, because we do end up doing about fifth roots. Let me see if I can pull one of those up real fast, or I'll just kind of make one on the side just real fast. So what I'll actually do is make a Excel table that has the number squared, the number cubed, the number to the fourth, and the number to the fifth. So obviously I don't want to start with 1. But then like for 2, 2 squared is 4 times another 2 times another 2 times another 2, 3 times 3 times 3 times 3 times 3, right? It's actually really helpful to have these up until like I'd say at least through maybe 15 or even 20, just so that you can see in this list here, oops, this row would have all your perfect squares, but this would have your perfect cubes and your perfect fourths and your perfect fifths, which we may not be as familiar with. So I would actually encourage you to stop for a second and make a list of those, because we are going to need them as we go through this this lesson and we start working on simplifying. Okay, so coming back over here, the fourth root of 81. Oh, look, that's on my list. Aha. Perfect fourth. 81 is a perfect fourth. Its fourth root is 3. The fifth root of 1024. Well, if I had made this list, I would have seen that if I had a positive 1024, it would be 4. But since I have a negative 1024, it would be negative 4. And the cube root of 825, we're basically going to think about what fraction do I multiply by itself 3 times to get an 8 on the top? That would be a 2. Note that up here. And 125, what do I multiply by itself 3 times to get 125? Would be 5. Okay. So if you're not convinced you need this list of numbers now, or if you weren't convinced before, maybe you are now. Okay, so that's just the idea behind higher power roots. answering a couple of quick questions. Every positive number, if I'm taking positive number, has how many even roots? Like how many square roots does 4 have? Does 3 have? Does 9 have? It has 2, right? And 1 is going to be positive and 1 is going to be negative. So that carries on to even roots, 4th root, 6th root, etc. 0 has always only one root, and that would be 0. The 3rd root, the 4th root, the 5th root of 0 is always 0. And negative numbers do have odd roots. You can take the cube root. You can take the 5th root of negative numbers, but they do not have even roots. You cannot take the square root or the 4th root because 2 negatives times each other is a positive. 4 negatives times each other is a positive. So you cannot take a 4th root of a negative number. Right, we've talked a little bit about these rules for radicals as well. We talked about them with square roots, but they do apply to any root. So we're just writing the index as n to be general here. So if we are rooting a fraction or a quotient, we can take the root of the top over the root of the bottom. If we are taking the root of a product, we can take the root of each one and then multiply them together. And here it is once again. This has come up multiple times. I put it on the first assessment, but you just want to make sure that you realize that you can just take the root of each one, does not apply to addition or subtraction. These expressions are not simplifiable. You cannot break them into further individual roots. So in other words, if I have the cube root, let's say, of x cubed minus 8, I cannot write that as x minus 2. It's not true that that is the case, okay? And then the nth root of a to the n, okay, is actually equal to the absolute value of a for even roots. And it's just a for odd roots. So let me just give you a quick example to show that to you. Let's say if I'm doing an even root, let's just do a square root. Let's say a was -3. And so then I'm going to square root -3 squared. Well, our order of operations would tell us to do the square first. So I would have the square root of 9. And the positive square root of 9 is 3. You'll notice that's not what I started with. So you're always going to get out of this expression, if it's an even root, a positive number. And so that's why we put the absolute value, because if we started with something negative, it will come out positive. However, if it's a 3rd root, then I'm going to cube the -3 to get -27, and then the cube root of a negative is a negative. So I do get what I started with. So we often talk about the fact that the power and the root cancel each other out, but for even roots, we need to keep in mind that that's actually going to give us the positive version. A lot of times in a textbook or a homework system, they don't make you write the absolute value because they say, we're going to assume that we're using all positive numbers, which is fine until you get to a point where it really does matter. So in general, we're probably going to go straight from here to an A and not an absolute value of A, but we do need to keep in mind we're making the assumption that we're dealing with positive numbers in that case. All right, let's talk a little bit about simplifying. We've done this already with square roots, so we know the general idea. You're trying to rewrite the radicand, the thing under the square root, as something that's raised to the same power as the root index. So if you can do that directly, like for example, in this first one, the 4th root, sorry, having technical difficulties yet again, of something to the 4th, okay, then we'll be able to just cancel out the root and the power. So certainly we can rewrite as u to the 4th. And what what do I multiply by itself 4 times to get 16? That would be 2. And so now the fourth root and the power just cancel each other out to give me 2u. Now, here's where I'm saying technically it should be 2 times the absolute value of u. But what happens is a lot of times there's going to be this caveat, assume all variables are greater than 0. And so that's why we use this answer. But technically speaking, if you didn't see this, it would be this. Okay. So similarly, I'm just going to kind of follow along the same idea. Can we rewrite what's under this fifth root as something to the fifth? So if you've made your list, the 243 is 3 to the fifth. And what power of u would I need to put here so that when I raised it to the fifth power, I'd have a 35? Power to a power is a multiply, so I would need u to the seventh. Then my fifth root and my fifth power would cancel out, and I'd get 3u to the seventh. Technically this, but a lot of times we go with this assumption. Okay. So one more there to try. Can you rewrite this cube root as something cubed? Oh, you know what? Let me go back real fast. Well, I'm going to erase these. Why don't I need that? What kind of root am I dealing with? Odd root. Sorry about that. If I'm dealing with an odd root, I don't need the absolute value. In fact, I should not use the absolute value according to my thing above. Sorry, I overlooked that. Won't make that mistake again. So I am doing an odd root here, so I won't need absolute values. All right, what do I raise to the third power to get 512? That would be an 8. And v to the third would give me 9th. So again, that would just simplify to 8v cubed. So that's the way to simplify a perfect square, cube, fourth power. But what if it's not perfect? We're going to get to that in a quick second. You'll notice, though, that I do have a question about a shortcut here. Can you see a shortcut related to the exponents when simplifying a radical that is evenly divided by the root index? So in other words, do you see, let me use 2 and 3, or you can even use 1 here, a shortcut between my answer here was u to the 7th, and I started with u to the 35th to the 5th. Or sorry, u to the 35th, fifth rooted. How do these numbers relate to this one? Does that continue here? I had a 9th power cube rooted, ended up in a third power. It's division, right? 35 divided by 5 is 7. 9 divided by 3 is 3. 4 divided by 4 is 1. Okay. So what you're really seeing as a shortcut here is that you can divide the exponent by the index. So the cube root, let's say, of x to the 12th would just be x to the 4th, because that would be the 12 divided by 3. So that is a shortcut you can use, and you're going to see when we get to the exponent part of this why that is true. Now, carrying on with what I had asked a minute ago, if you cannot rewrite the radicand as a perfect cube or a perfect fourth or whatever the power is, then we're going to follow the same steps we did with radicals, square roots, to simplify. And that is basically we're going to break it up into the product of something we can take the root of times what's ever left. So step 1, we'll break the number, we'll do the number separate from the variable, into the product of 2 numbers. So one of which is a perfect cube or a perfect fourth or a perfect fifth. And that's where that chart I was just talking about is going to be useful. And then you can also break the variable into a product. And what you want to do is use the highest exponent that's divisible by the index. So if my index is 5, I want to break it into a product of w to the 5th or w to the 10th or w to the 15th times whatever would be left. Then you can rewrite as a product of radicals and take the root of the two things that you can take the root of. So let's take a look at an example. So first of all, I have a 5th root, and I need to find, I have 160, right, as my number. Well, 160 is not a perfect 5th if you're looking at a chart of numbers. But if I'm looking down a chart of numbers, I will see that 32 is a perfect 5th, and 32 goes into 160. So what I usually do is I just take my calculator and I just start dividing. 160 divided by 32, which is the first number there. 160 divided by 243, which is the next number there. I mean, I just keep going down the list of numbers until I find the largest one that divides in. So 160 was 32 times 5. And then I'm going to move over here to the w to the 8th. Because my index is 5, I want to break this w to the 8th into w to a power divisible by 5, which will be 5 times whatever's left, which would be 3. So I can't use w to the 10th because I don't have that many. So I have to use w to the 5th. I'm looking for multiples of 5 to put here. Now I can take the 5th root of these two things. The 5th root of 32 is 2. The 5th root of w to the 5th is w. And then I just have to leave the remaining things underneath the radical. So there is my simplified radical. Okay, let's do one more. Then I'm going to have you try the last one on your own. So now I have a cube root. So I'm looking to rewrite 16 as a perfect cube times whatever is left. So 16 is 8 times 2, and 8, the cube root of 8 is 2. And then I've got v to the 14th, and I'm looking for a power that is a multiple of 3. So I could use, the highest one would be 12, right? V to the 12th. And I would need an additional 2 more to make it up to 14. So again, these two are cube rootable. Cube root of 8 is 2. Cube root of v to the 12th is v to the 4th using our division shortcut. And so then what's left is the 2v squared underneath. So go ahead and give this last one a shot. Pause the video and see what you can. All right, how did it go? I saw that 81 is a perfect 4th already, so I don't need to break it up. I'm just going to leave it there for now, and I'll take the 4th root of that. T to the 15th, since I'm looking at an index of 4, the multiple of 4 that's the greatest multiple of 4 less than that would be 12. So I have t to the 12th times t to the 3rd. And 18 here would give me w to the 16th times w squared. Again, 16 being divisible by 4. So I've circled the things I can take the root of, taking the root of them outside. So divide by 4 on your exponents here. And then I just leave the remaining factors underneath. Okay, so now we're going to kind of extend our shortcut now that we've done it this way. And there's nothing wrong with rewriting it and doing it this way the whole time. But you might have noticed that we can kind of apply the shortcut we used, which is if I divide the 15 by the 4, I get 3, right? 15 divided by 4 is 3 with a remainder of 3. And so 3 comes out and 3 stays in. 18 is divisible by 4. 4 goes into 18 4 times with a remainder of 2. 4 comes out, 2 stays in. So you could use that as a shortcut instead of actually rewriting every time. If you like to rewrite it, go for it. But if you want to, you can try this shortcut, which would be divide the exponent by the index. The quotient, that's kind of the answer part of the division, will be the exponent outside the radical, the part that you pull outside, and the remainder will be the exponent under the radical. So again, we're not making up some math magic. We're just looking at the pattern of how these exponents and the simplifying process works and finding sort of a shorter way to do it rather than writing it out the whole time. But there's nothing wrong with writing it out. So I want you to try these next 4. Go ahead again. Same thing. I'm just asking you to simplify and do it whichever way you like. If you want to write them out, you can, or if you'd like to use the shortcut, then give it a try. Pause the video and come back. All right. So for the first one, the third root of 64 is just 4, and 6 divided by 3 is just 2. So nothing stays underneath the radical. Same thing with number 5 on the 162. I can break that into 81, 81 times 2. So I cube root the 81 to give me the 3 outside, and the 2 stays underneath. And for the V, 13 divided by 4 is 3 with a remainder of 1. 27 is not divisible by any fourth roots, so it stays firmly under the square root. But 10 divided by 4 is 2, remainder 2, and 17 divided by 4 is 4, remainder 1. Last but not least, 160 was 5 times, I lost my number there. Where did it go? 32. That's what I was looking for. I don't know why that one took me a while, but it did. 32 times 5, so the fifth root of 32 is 2. 5 stays underneath. 18 divided by 5 is 3, remainder 3. 20 divided by 5 is 4 with no remainder, so no W's left underneath.